So good morning to all of you. In the last class, in the last class, we started learning about this magnetism in solids. How does the magnetism originates in solids, and the classification scheme. What are the different types of magnetism that can be found in different type of materials? So looking at the pure elements, these were the four types of magnetic properties that you can find: ferromagnetic, paramagnetic, antiferromagnetic, and diamagnetic in elements in pure state. Okay, so what we found that there are only three elements which are ferromagnetic. Sorry, what happening? What is that? Iron, cobalt, and nickel. These are ferromagnetic. So, as in a pure elemental state, whereas only one element is antiferromagnetic, and then most of the elements that we see are either diamagnetic or paramagnetic. So that's so overall you will find that in the periodic table there is a dominance of paramagnetic material. They are greater in numbers, uh, as you can see in this slide. And then this behavior that yeah, based on that we classify them: diamagnetic, paramagnetic, antiferromagnetic. And then there is, as I was telling you yesterday, there is fifth type of magnetism, which is not found in pure elements but in mixed oxides. So that is typical of ferrites, like Fe2 or Fe3O4. Magnetite is one of the example of that, and that was it is, and that's why the name ferrimagnet, a magnet type of magnetism that is found in ferrites is ferrimagnetism. Simple. So name, ये नाम वहीं से आ रहा है, फेराइट से. फेरी जो पार्ट है इसका, फेरी मैग्नेटिज्म, फेरी is coming from, the prefix ferri is coming from ferrites. So based on, so the value of magnetic susceptibility is different for all this, that we can find through this graph, through this table. So this summarizes the whole thing about the magnetism that exists in different forms, and what kind of material, what kind of curves, what is the susceptibility range. So based on that you can clearly distinguish between these features, between these properties. So diamagnetism, there is no spin, as you can see. You have no spin existing in when there is no field applied. It is a spin paired system and no magnetic moment. Susceptibility is very small and negative. So negative graph, you can see negative slope. Paramagnetic, in contrast, is having a positive slope in M versus H curve. Okay, so initially the spins are random, they are randomly oriented. So overall there is no zero magnetization when there is no field applied. When there is no external magnetic field, the field is zero, because although atoms have individual magnetic moments in the crystal, the overall magnetization is zero because of the random orientation. But as you apply the external field, these spins start getting aligned. They start getting aligned with the magnetic field, and you see a rise in the magnetization value. So that is a typical curve for paramagnetic materials, where you find a straight line in M versus H curve with a slope that is much larger and positive. So this is the slope gives you the susceptibility. susceptibility is plus 10 to the power minus 5, a positive value and larger value. Ferromagnetism is in susceptibility is very large, and you have aligned spins even in the absence of magnetic field. Not all will be aligned together, but there is net magnetization remains in the crystal even if the field is removed. So that is the kind of thing that you have for the ferromagnetic material. Okay, then anti-ferromagnetic, there are certain compounds like in transition metals we have chromium, manganese, that exist as anti-ferromagnetic. So MnO, cobalt oxide, nickel oxide, these are the anti. So what happens in this is that there are spins which are aligned. There are some spins which are aligned parallel to each other. There are other area atoms on which the spins are anti-parallel. So if you look at the overall picture, the net, when there is no field applied, or if you apply the field and remove it, you'll find that net magnetization would be turn out to be 0. So this is the anti-ferromagnetic behavior that you see M versus through the M versus H curve. And in ferrimagnetism, it is similar to what we have seen in case of ferrimagnetism. Let me just enlarge it for the better view. So in case of ferrimagnetism, what will happen, that there are sites where you have opposite spins are not aligned like here, but they are overall, if you look at the crystal, such opposed spins which are anti-parallel are less in number, so that overall there is magnetic moment. Okay, atoms have mixed parallel and anti-parallel aligned magnetic moments, but there is uh, it is not exactly cancelling out. In case of antiferromagnetic, we saw that it exactly cancels out, and when on removal of field it is 0. The magnetic field, the magnetization M becomes 0. But here the net magnetization remains, and if you look at the feature nature of the curve, it is quite similar to the ferromagnetic ones. So ferromagnetic behavior and ferrimagnetic behavior, if you are only observing MH curve, it will look almost the same. But when you look at the internal structure, then you find there are spins which are anti-parallel, there are spins which are parallel to each other, and so. But overall, these anti-parallel spins are not able to cancel out the parallel spins, and there is net magnetization present. So susceptibility is still very large as compared to paramagnetism, but it will be maybe slightly lower as compared to ferromagnetic. So we start learning about more about these ferromagnetic materials, and the basic feature that we are talking about is the parallel alignment of spins. So these are the atoms, and on these atoms you have a spin of the electron that is getting aligned with the external magnetic field. And once you apply magnetic field and remove it, it still remains. The alignment, some of the alignment still remains, giving you overall a permanent magnet kind of thing that is you can think of. So there is strong interactions between the atomic moments that you can see as compared to paramagnetic materials. It is very strong, and this is mainly due to the exchange process, the Hund's rule that you have already learned. and more you will be learning in the term symbols, where we are going to talk about the Hund's rule 1, 2 and 3. So exchange interaction is typically described through that. So a set of parallel spins is usually lower in energy because of exchange energy. So so depending on the situation, the exchange forces align have a result in aligning these atomic moments at certain times, or sometimes they become anti-parallel, depending on the situation. So what happens? This exchange forces, the extent of magnitude of the exchange forces, if you compare, it is very large. It is very short range, exists, but it is very large, about 1000 Tesla, or about 100 million times stronger than the Earth's magnetic field. So 1000 Tesla is a very big number, considering that if you think of a strongest magnet in the world, that was 50 Tesla, that is in the US, 45 or 50 Tesla is the maximum that a human beings can make, till now have been able to make. So it's when we look at this, that the 1000 Tesla, that is huge number. Okay, so it is relative to the spin quantum mechanical treatment exchange force you can get in a spin of two electrons. So ferromagnetic materials exhibit parallel alignment of magnetic moments even in the absence of magnetic field. So iron, cobalt, nickel, ferromagnetic materials, we all know. So there are two distinct features: spontaneous magnetization, that and the existence of magnetic ordering temperature, a temperature below which they can there will be alignment of the spins, and at a certain temperature, very high temperature, it may happen that all the spins get randomized. They will become random. There will be no alignments. That is the Curie temperature. We will discuss it in a small while from now. Spontaneous magnetization is the magnetization that exists even in the absence of a field in a substance. The magnitude of this magnetization is at 0 Kelvin is dependent on the spin magnetic moment. So related term is saturation magnetization. We already talked about saturation. What is saturation magnetization? The maximum value of magnetization that can be achieved in a system is the saturation magnetization. So, when all the spins are aligned with the magnetic field, if you go on increasing the external magnetic field, there will be no further change because there are no spins available. All have aligned already. So that is the case of saturation magnetization. So maximum induced magnetic moment is your magnetization. So that's the thing that I was trying to tell you. This is the magnetization applied field, and this is the saturation value. There is no change with respect when the applied field is changed. So this is how it is. So this spontaneous magnetization and other things, saturation magnetization, we will understand these things in terms of magnetic domains in a later. So the terms that you must be familiar of: saturation magnetization, and it is intrinsic to any substance. That is, this property is there is no effect of particle size. and the susceptibility, if you so paramagnetic, we have already discussed in the table. While discussing that, paramagnetic susceptibility is less, ferromagnetic susceptibility is much higher in comparison. So saturation level in ferromagnetic materials you are able to see at, because that occurs at a moderate magnetic field. But in case of paramagnetic, as you can see, there is no saturation. In case of paramagnetic, under the same conditions, where they have given pictures. Okay, not here. Huh. Yeah. In paramagnetic material, you see saturation magnetization. Yes, you can achieve saturation at a certain value of applied magnetic field, which is reasonable. But for paramagnetic material, you will find that it is not saturating at around the same magnetic field. But maybe if you apply a very very large magnetic field, then that can also saturate. But so that is the point to be made here, that saturation magnetization can be obtained by applying the magnetic field. And then why this is not coming? Okay, so this is a typical. So beyond the point of MS, so we denote it by MS, writing MS. So typical ferromagnetic elements: iron, nickel, cobalt. That's what we were discussing. And the two features of these ferromagnetic materials are spontaneous magnetization and magnetic ordering temperature. So spontaneous magnetization, when we talk about this, अपने आप जो इसमें exist करेगा, that is in the absence of magnetic field. That is one. Magnitude of this magnetization at 0 Kelvin is dependent on spin magnetic moments. So what you measure in the laboratory is the saturation magnetization, and yes, so okay, so sorry, just a moment please. Okay, so yes, there's no change in the, so that is what we saw already. And so this was the behavior of a magnetite. So this is a typical behavior of a magnetite crystal of very small size, of few of 35 to 40 microns. And so saturation magnetization is under some force, applied magnetic field, and spontaneous magnetization is the magnetization that is in absence of any field. So this is the prime difference between the two that we are talking about, and it is related to domains. We are going to talk about it in very soon. We will understand why domains exist, so that discussion will come up. So there is a difference in the susceptibility. There is when you look at the susceptibility values. Again, it is screen is getting cut. I don't know why this happens, but it happens somehow. So I have to rearrange this stuff here. Okay. So the susceptibility that I was talking about. Look at the value of susceptibility for paramagnet. It is 50, and ferromagnet is 1000 to 10,000 meter cube per kg, 10 to power minus 8 meter cube per kg. So this is the order of difference, 50 compared with 1000 and 10,000. So paramagnetic, so small change in magnetic field. There is huge change in the magnetization value for, there is a significant change, very large change for ferromagnetic material as compared to paramagnetic. You will get as compared to paramagnetic. So paramagnetic materials have less change in the magnetization value. And the other difference that you see, that saturation, at what value of externally applied field you achieve saturation magnetization. So ferromagnets saturate at early around 1 Tesla, whereas paramagnets magnetic material will not saturate at the same scale. It will require at least 10 times or more than 10 times the magnetic field as compared to a ferromagnet. So these are the essential features. You also have the range in which this magnetic properties can be observed. For ferromagnetic, around room temperature you can observe. For paramagnetic behavior, it is less than 100 Kelvin, sorry, you will be able to observe these properties. So this is the situation. So what you see here is the lines that we have is drawn and a big arrow, thick arrow. So there are several electrons present in, so this is a crystal, and there are several areas within a crystal where certain atoms have spins which are all small, all are pointing in one direction. So this is what we call, and summation of this is shown as a thick arrow. So all are pointing in the same direction. So but there are several such areas where spins are aligned but pointing in some other direction, but they are, with respect to each other, they are aligned. So you have several electrons present in this area. So actually they are lying on the different atoms, but overall situation is that there is no net magnetization. So that is the situation when the, suppose if you have just synthesized ferromagnetic material, that will be a situation. Then what happens is that when you are applying the external field, so this is the external applied field H, applied magnetic field, then what you are seeing, the case of the maximum value ms. So this is 0 magnetization, and this is the corresponding to the picture corresponding to the saturation magnetization. So all these domains, so this boundary, the line that separates an area of similar type of alignment of spins with the other type of alignment of spins, that is called a domain. And the boundary that we call is the domain boundary, domain wall. This is a domain, and the line that we are drawing is will be called domain wall or domain boundary. Both can be used. So this is the thing that happens when you have place an iron, uh, say iron crystal in a magnetic field, and gradually slowly increase the magnetic field. So the magnetization, so because this application of the magnetic field produces, the effect is the alignment of these spins in that direction, and that is the thing that yeah, you get increase in the value of magnetic overall magnetization, that is. So there is a animation that we can see. It is the, so this is National Magnetic Field Laboratory, High Field Magnet Laboratory, that is in USA. So National High Field Magnetic Field Laboratory, look at this. So you can also go through this website, which is good for learning the basics of magnetism. Okay, In short, we call it MagLab. Actually, I happen to have worked there in the US National High Magnetic Field Lab during my postdoctoral work. So this, you can see, is the basic idea of the ferromagnetic material and the domains that exist. You can get from this in a very simple way. It is presented in a very simple way with animations. So you can see this is the magnet. Look at this. This is the magnet, and this is your material, ferromagnetic material, in which you have several domains. So this white arrow that you are seeing, the white arrow in each of these areas that you see, it is a collection of, it is a vector, sum of the vectors or spins of several electrons in that area, okay, which are pointing in the same direction. Okay. So this is the thing. So what happens? So look at this. When I bring the magnet closer to this ferromagnetic material, so you will see, bringing closer, closer, you will see a change. एक मिनट reset करते हैं. So when we reset random and then we start, so let me just zoom in. Yeah, now it is the center of the screen. Now you can see better. So this is the random, in absence of magnetic field, this is the situation. Now when I bring this magnet closer, see, the domains are now, that white arrows are now changing directions. Can you see that? Gradually, yeah, yes. So when it is moved further, they are getting aligned till the maximum. So this is what we mean by increasing the magnetic field. So actual field that the materials feels is increasing gradually as we bring it closer, closer, and finally the maximum is achieved when it is the closest. So this is the alignment that you can get maximum, and this will correspond to the maximum value of magnetization achieved in this sense. So you can play around with this in your free time and learn more about this. So you can just zoom out from this. Okay. So going back to this ferromagnetic material. So yeah, just okay. So that was the point. So this is the link of the National Magnetic High Magnetic Field Lab in US, in Florida. Okay, and that's what I was telling you, that the strongest magnet they had built. अभी का तो पता नहीं, उस समय तक जब मैं 2009 2009 में गया था, तो स्ट्रॉन्गेस्ट मैग्नेट था इसी जो कि इन द वर्ल्ड वाज दे हैड मेड, दैट वाज 45 टेस्ला. सो सोचिए, टेस्ला जो यूनिट है वो बहुत बड़ा यूनिट है. उतना जो हम 1000 टेस्ला की एक्सचेंज फोर्स की बात कर रहे हैं, वो बहुत ही स्ट्रांग फोर्स, स्मॉल एक स्मॉल एरिया में हम बात कर रहे थे. जो एक मैग्नेट आप बनाएंगे तो 45 टेस्ला वाज द मैक्सिमम दैट कुड इन द वर्ल्ड दैट कैन बी अचीव्ड. परमानेंट मैग्नेट अगर आप बनाते हैं तो, so that is the order. So usually it is very small, a fraction of Tesla that we use in normal circumstances. So thermal energy. Uh, so what happens is that, suppose you have a ferromagnet and you start heating that material. you have applied the magnetic field and you got some alignment of spins. The spins are getting aligned, and now you start heating them. What will happen? They will get energy, and they will be, so whatever ordering you had achieved, that will change. They will start becoming random. More randomizing effect will be there. So with increase in temperature, if you already suppose you have achieved the saturation magnetization and then you start heating the sample, heating the material, the spins will, because of the thermal energy, the spins will become random slowly, and as the alignment will not be there, and gradually you will, the value of magnetization will decrease with increasing temperature, and at some point all the magnetization will be gone. So that point is the Curie temperature, where the order that you had achieved when you apply the uh, applied magnetic field to achieve maximum saturation magnetization, that we call, that starts decreasing, and finally it becomes zero at some temperature, because of the random, you are putting energy into the system, and because of increasing thermal energy, the spins again get disordered, and just they'll be totally random at some point at some temperature. So whatever ferromagnetic behavior that we talk about is below that temperature, Curie temperature. Above it, it is disordered. Above that temperature, it is there is total disorder, and you will not observe the ferromagnetic behavior. So saturation magnetization becomes zero at Curie temperature, and the graph. So graphically, we can show this like this. So this is the for magnetite. So you can see here. So you have saturation magnetization achieved at some temperature. So this is the ratio actually of magnetization at the temperature, at a given temperature, and magnetization at 0 Kelvin. So compared to that, so 0 Kelvin, you can expect maximum order in any substance. Thermal energy is 0 at that point, and so there is, and as the temperature is increased gradually, this is the saturation magnetization at 0 Kelvin. Okay, and this ms decreases as as temperature increases. So this is to see, so this is the so as the temperature increases, it is going on decreasing. There is more randomness, you can see, spins getting random, spins randomized, randomized, or you say disordered. There is, so order that was achieved earlier at lower temperature is now getting gone, and finally at some point it will become zero. So that particular temperature is called Curie temperature. So Curie temperature is intrinsic property, and it is used for identification of minerals also. Hmm. So this is, so everything, that behavior that we are talking about, alignment of spins and saturation magnetization, we are essentially talking about below the Curie temperature, where ordering spins are in order in a particular arrangement. There is a arrangement, alignment is there, and above this temperature all that order is gone. It is totally random. So after this point, so we can also, so this saturation magnetization you can compare at absolute zero, that is at 0 Kelvin. What So europium oxide 1920 Gauss. Gauss is the unit for magnetization, is represented. And you see the Curie temperature. Curie temperature is located in this column. So 69 Kelvin is the Curie temperature. So that, what does this mean? This means that europium oxide will not show ferromagnetic behavior above 69 Kelvin. So at room temperature, when you are looking at magnetization at room temperature, nothing. You have nothing over here. Also note the point for iron, cobalt, and nickel. 3d6, 3d7, 3d8. So that's the 3d6, 7, 8. So what do you see here? That yes, you look at the Curie temperature 1043 for iron, 1388 for cobalt. That means up to this temperature, below this temperature, there will be spin alignment, spin ordering, and you can observe the ferromagnetic behavior. So 0 Kelvin, you have a very good ordering, so very high value of magnetization. At room temperature, it is slightly less. So 0 Kelvin and room temperature, you can compare. So in case of iron and cobalt, even at room temperature, you have a very significant value of saturation magnetization as compared to 0 Kelvin. It is less than 0 Kelvin, but बहुत ज़्यादा कम नहीं है. वो 1446 है, तो ये 1400 है. ठीक है, ये 1740 था, ये 1707 है आयरन के केस में. So like that you can see that it is the value that you are getting, if you calculate the magnetization that you are observing, it corresponds to 2.2 number of electrons. When you calculate for cobalt, it is turned out to be 1.7 number of electrons, and so on. So whereas in European you are getting 6.8, which is close to 7, almost 7. So 7 electrons in the 4f, like that you are getting. So so things are like this. We'll learn about. So what we have so far learned is that yes, magnetization becomes 0 at Curie temperature, saturation magnetization. And if you look at the same ferromagnetic material and look at the what happens to the susceptibility, we can also find what happens to the susceptibility as the temperature is increased. So susceptibility chi, what is chi? This is equal to dm by dh. Okay, so that was the thing. So so if you follow the value of susceptibility, so ferromagnetic materials will show a decrease with temperature. And at this point, Curie temperature, this is Curie temperature, where I said that there will be no alignment of spin, there will be randomization, they will behave. So above this temperature, above the Curie temperature, they behave as a paramagnetic. So the curve after this point is that of paramagnetic. So we also say that Curie temperature is a point, as is the temperature, is that temperature at which a ferromagnetic material starts showing paramagnetic behavior. A ferromagnetic thing converts into a paramagnetic material. So that point of conversion of ferromagnetic to paramagnetic is Curie temperature. That is also another way to look at it. So this thing we are able to find when we discuss the susceptibility with respect to temperature. So this is susceptibility with temperature. So this is the behavior. So what we found that yeah, this point also I discussed yesterday, the hysteresis part. I told you that when you remove the magnetic field, it will still So hysteresis curve, so you get it retains the values. When you remove the field, still it retains a very large value of magnetization, even in the zero field, when the all field is removed, and that it traces a path that is a loop. You get a loop kind of thing. So that was, where is that thing? So hysteresis is the name of that curve that we obtain in M versus H. So that is the, I told you that if you start, you will get like this, and then if you retrace the path, it will go like this, something like this will appear. So this is the MS value, and this was the initial path that you had taken. Okay, so after that, if you try to, so this is the how you moved, then you reverse the direction of magnetic field, it goes to the maximum in the negative direction, it becomes zero here. So this was the, so this kind of curve that you get is the hysteresis. We say that remember what has happened to it. So when you remove the field, this was the maximum saturation magnetization, and this is the MR remnant, the magnetization that remains even after the field is removed, external field is removed, and you still have the some substantial value of magnetization remaining. So that is what we mean by hysteresis, this M versus H loop that you get, and we call it hysteresis loop. So this is a typical feature of the thing. This is HC, coercive field, the field applied in the negative direction, uh, in the reverse direction, to make the magnetization zero in the sample. So that is called coercive field. So all these things are given in the later on in the slides, and even sometimes before. So that is the essential feature of these ferromagnets. So coercivity, I told you, coercivity of resonance is the same thing. You have to apply a force, magnetic field, in the reverse direction to make the saturation magnetization to zero. So initial susceptibility, so you can also see that it is not a very straight line, and so the magnetization, the susceptibility, the slope will be different at different points. Initial susceptibility is the point when you are just starting, when the magnetic field is closer to zero, tends to zero, and what is the magnetization that you change in magnetization with field. So initial magnetization is the in the order of Earth's magnetic field, very close to 0 point. So when here we have graph, yes, this is the graph. So at this point, so dm by dh will be different starting point. This is the chi slope, dm by dh at 0 point, so at the origin. So that we mean, what this is what we mean by saying, just chi 0. So saturation magnetization at origin, at the point 0. So that was the point that it is on the order of 50 to 1000 micro Tesla. Uh, so there, so what we will discuss next is that it, the properties, the hysteresis, the loop that we are seeing, it will depend on the size of the crystallite size, the small crystallites that are present, and the domain state, stress, temperature. All these factors will affect the overall magnetic behavior, and this is what happens in the when you apply magnetic field. Suppose you are gradually increasing the value of, so from this side to this side, H increases, So applied magnetic field, H is what? Applied magnetic field, and you are increasing this. So H increases applied magnetic field. So the direction of field, this is the applied magnetic field that you see in the gray. This is your H, this arrow, this big. Uh, so applied magnetic field is gradually increasing. So you can see the drawing. So see how the drawing has been done. The number of arrows gradually increase. ये वाला arrow देखो धीरे धीरे बढ़ता जाता है लेफ्ट टू राइट वाले पिक्चर में. अब सब्सटेंस के अंदर में देखो, लुक एट द इनसाइड ऑफ द सब्सटेंस. So do you note these points? See, 1 2 3 4 5. So 5 such arrow here. So this is what you call, this is your H, and this is also your H, the magnetic field, applied magnetic. So 1 2 3 4 5 6 7 8, whereas in this case you have even larger number of. So this is to indicate that we are gradually increasing the magnetic field when we move left to right. So these are the things that I call scientific drawing, very conveying the idea that we are increasing the external magnetic field. So this is external field applied, and this is gradually increasing from left to right. So what happens here is that initially what you find is that we have areas of different spins aligned in this direction. So see, this is one. Then there's also area where they are pointing, spins are pointing in the other directions, but they are within that particular area, they are all pointing in same one direction. So that is one domain. So pointing up one direction, pointing diagonally, there's another area, so that is another domain. And this line that separates these domains is called domain boundary or domain wall. So what has happened here, as the field is increased, you see, so this shaded area, the yellow color shades, that has increased. So some of the more, what has happened, that these spins, these spins have also converted, aligned with the field, and so the boundary, this domain is gone, वो खत्म हो गया. So this is what we call growth of the domain. One domain, so the domain boundary is now vanished because you were simply looking. ये कोई फिजिकल बाउंड्री नहीं है बनी हुई उसके अंदर, क्रिस्टल के अंदर, समझे? ये जस्ट हम इमेजिन कर रहे हैं कि ये एक एरिया है जहाँ पे एक जैसा स्पिन है, दूसरा एरिया दूसरे जैसा स्पिन है. तो अगर दूसरा वाला स्पिन भी अलाइन हो गया उसके जैसा, तो वो तो एक उसी का हिस्सा हो गया ना. दैट इज, सो इट इज वन डोमेन compared to that. So in a similar fashion you can see here that initially you had, these were the area we were looking at, and when the magnetic field is applied, you see all these things which were pointing in different direction, now they are also getting aligned. So this is now the domain boundary between them is gone, and this domain which was having spin aligned to the field is growing. What you have seen from the picture 1 to picture 2, look at the shaded area, yellow color shading. What we say that there is a growth of the domain. The domain that is already having spins aligned with the magnetic field is now becoming larger in size, and the others, so how does it become larger in size? Because some of the nearby domains, nearby spins which were in different direction, has converted into the same direction. The spins have oriented and aligned with the field, so it has grown at the expense of other domains. ठीक है? And gradually when you finally, if you continue doing so, so you can look at this picture here. It was like this, and this was a domain which is now completely gone. they are all these things have aligned in the same direction, and so we are counting them to be a part of this domain, which is increasing in size. Increasing in the domain is increasing in size, that is growth of the domain. The boundary between the two domains are now gone, and so gradually, if you continue this situation, keep on moving, go on increasing the applied magnetic field, a situation will come when all of these other white shadings, these all will get aligned with the magnetic field, and you will have a single domain. So from a multiple domain to a single domain, entire particle. So when you are achieving saturation magnetization, so this is the situation when you say that we have achieved saturation magnetization, and that is this when all the spins are aligned in one direction, in the direction of the magnetic field H. So in the direction of magnetic field they are all aligned, and that is giving a maximum value of magnetization. So initially we started with multiple domains, 1, 2, 3, 4, or 4, 4, 5, 6, 7, 8, 9, 10. So initially you started with 10 domains, 1, 2, 3, 4, 5, 6, 7. 7 domains, and this is only one domain you have. So this is what happens. So यही पिक्चर जब आप हिस्टेरिसिस लूप देख रहे हैं ना, वो वाला हिस्टेरिसिस लूप का जो पॉइंट देख रहे हैं, यही चीज होती है. So you have a large number of domains initially, in several small areas, collection of several areas. Each one of them has spins aligned in different direction. They are not all pointing in one directions. Within one area they are pointing in like this. So like this is the situation. Then as you gradually increase the magnetic field, the domains which are already aligned with the field will grow in size, and the adjacent domains will shrink. That means that the atoms with the spins uh, uh, nearby atoms will also start getting aligning with the magnetic field, and so that's how we are counting that shaded region as a growth of the thing. So this is what happens. To make it much clearer, one more, I will draw this thing over here again to highlight this point M versus H. So if I can show this here, sorry, so let me put it like this, M versus H. So this was M, this was H, right? And you were starting showing like this and achieving this point. So this was the point that we were showing, that you gradually you achieve saturation, sorry, so initially it is 0, then increases and you achieve saturation. So this was the, so this is the point. So MS, so this area is the situation. So this situation is represented by this picture, and the somewhere middle point that is represented by this picture, and the initial picture so initial thing is this one. Okay, starting point, you have some overall spins are random, then at some point in the middle you have growth of this thing happening, and gradually you are moving to that part. So saturation, middle. So that is the situation that you have to understand. ग्राफ से ये सारा चीज रिलेट कर पाएंगे. So saturation जब आ गया, so this is the point of ms. ओके, सो दिमाग में ये पिक्चर चलता है हमारे जब हम स्पिन्स को देख रहे हैं कि जैसे जैसे एच इंक्रीज कर रहा है. सो दिस इज व्हाट वी मीन व्हेन एच इंक्रीजेस, gradually the spins are getting aligned. If you look at the domains, some of the starting from a multiple domains system, it is finally becoming a single domain system. So the domains are growing. The domains which have the spins already aligned with the magnetic field, they continue to grow at the expense of other domains which are not aligned. Okay, so this is the situation that we were talking about. So A, B, C, D, E, each of these points you should be able to explain. Start from here, then move up to this, then reverse, go to this path. Okay, so continue going. So this is the B is the, so this is the saturation magnetization ms. This is mr, remnant magnetization, which remains, magnetization that remains even after removing the magnetic field is remnant magnetization. And this, so to make that magnetization zero, you need to apply force in the negative side. So this is the HC, coercive field. So this is the situation that has been discussed, and pictures tell you the story that we have already discussed. Okay, so C and F are the points where coercivity points, C and F, minus HC plus HC. That's how we talk about this. This is saturation on the positive side, saturation, positive side, and saturation. This is the point of saturation. So this is the minus side, ms, negative side, like this. So this is how a typical hysteresis looks like, and the microscopic view of the spins, how it changes, that also I have given. So this is these are the points that you should note. We have already discussed. The material start from this point. So the dotted line means that it is only one time that it will happen like this with a ferromagnetic material, that it will follow this path. After that it will retain this value, and no matter how many times you do this, it will keep on moving along this path, that dark lines. So that is the thing. So this is the thing that will happen to it only one time. This will happen only one time. One time affair, first time when you subjected to magnetic field. उसके बाद जितनी बार भी आप करेंगे तो ये वाला लूप फॉलो करेगा. It will follow this loop again and again, no matter how many times you increase or decrease the magnetic field, reverse the direction. ये जो dark lines है वही वाली arrow follow करेगा. और it is only the first time a material when it is subjected. So it is a non-linear curve that you are seeing. One, you are getting, so the pictures are now clearer. So I have discussed already all these points, so nothing more to add. It is just that it is written here, given to you. And so there is one more microscopic view that I can tell you what will happen here. So look at this. This is the direction of externally applied field, and this is the material. So more uh, ferromagnetic material, ferromagnetic material. So suppose the domains are like that. Okay, so this is the, please note, left to right we are moving. What is the situation, what will happen? So look at this. This is the direction of externally applied magnetic field, HEX, right? Note that. And now look at the ferromagnetic material. It has domains. So four domains that you can see, and only one of them is, this domain is particularly having it is not aligned to the, it is not really aligned to the external magnetic field, but it is closest to that situation. Okay, it is closest to the HEX. So what will happen? This domain will start growing. See, this domain, it grows in size. Oh, sorry, what happened? So this domain 1, let me label it as A, B, B, C, D, A, B, C, D. So the domain A grows in size. You can see that domain A, it is growing in size, that is, and the nearby adjacent domains have become smaller. So some of the spins in the adjacent domains have are getting aligned with this, and finally you will get all of them, it will become single domain, multiple domains. So what you are seeing here again is that it is having multiple domain, 4 domains, then one of the domains, domain A, grows in size, others, what you see that other domains shrink, they become shrink. Oops, that image, sorry. So other domains, एक domain जो है वो बड़ा होता जा रहा है, others shrink, and finally others are gone, only one domain. So this domain is, so only a single domain is now there, and now you have to now it will rotate. So domain, so what has happened, that domain wall has shifted. What you have shifted, a domain A has grown, matlab its boundary has changed. So we say that domain wall has moved. Okay, motion of the domain walls that has occurred, and finally we are getting a single domain, and which has spins which is pointing slightly away from the, it is making certain angle with the applied field, and so it will rotate, it will undergo rotation to align. So this single domain, once we have achieved, it will undergo rotation. So it is rotation that occurs. Sorry, एक मिनट, रब क्यों नहीं हो रहा? So what I can do now again, हाँ, so एक बार में चला गया. So what we are seeing, that after it is becoming single domain, it is rotation of the domain. So you obtained a single domain, rotation of the domain, and it is now getting, see the angle, ये pink वाले का और ये aligned with the domain, aligns with H externally applied magnetic field के साथ align कर गया. So from here to here what we saw is the growth of domain one of the domains and then achieving a single domain. Here we also saw two, we are also observing domain wall motion. So this has happened, domain wall moves, boundary changes, so domain wall motion. Okay, so there are two modes. What have you observed so far? There are two things that is happening. Domain grows, there is domain motion of the domain wall, and then rotation of the domain, motion of the wall, rotation of the domain. Okay, two things. So these events happen. So orientation in the field. So when you are reaching here, this if you further dissect the things, so between this pink and black, this situation is the rotation of domain. Just prior to observe rotation of domain, it is almost single domain has happened, and from this to this is the, from this point to this point up to this point, so whatever that we have observed is happening over here. Oops, क्यों नहीं चलता है ये जो है, ये पूरा हमारा डोमेन वॉल ग्रोथ ऑफ डोमेन, डोमेन वॉल मोशन, मतलब एक जो डोमेन है वो ग्रो कर रहा था, डोमेन वॉल मूव किया. So in summary, if I think so, rather than that I can write only two words: rotation of the domain and domain wall motion, motion of the domain wall. Rotation of the domain occurs at the final point once you have achieved a single domain which is almost near which is already very close in terms of alignment, but not yet aligned perfectly. It has, and final rotation, one rotation, and it will align. So that kind of thing happens near the saturation point, and before that all those things are happening. That is domain wall motion. So domain wall motion and rotation of the domain, that is these are the two things that happen. Okay, so that's how we understand this graph MH loop. And yeah, I think it. Okay, so we'll discuss more on this later. अभी बहुत कुछ है, and yeah. So why do the domains exist? That is the question that we will ask. We will understand next time.